Hi everyone, Israel Hamsi, technical engineer, and I'm delighted to welcome you to today's session on Docker. By the end, you will not only understand the concept of containerization, but also be able to build, manage, and deploy a small application using Docker. We'll begin with foundational ideas, so whether you're entirely new to containers or have dabbled in virtualization, there will be something for you. Let's unpack this. In traditional deployments, you develop on your machine, then move to QA, staging, and finally production, often encountering the universal "but it worked on my laptop" problem. Containers encapsulate everything your app needs, from libraries, binaries, to configuration, so you eliminate environment discrepancies. You can think of it like actual shipping containers. Standardized in size, easily stacked, and transportable across ships, trains, trucks without repacking contents. So when I say build one, run anywhere, I mean exactly that. You run your container on your laptop, on a colleague's machine, or on a cloud server, and it behaves identically. You might ask yourself, how is that different than setting up a virtual machine? Our virtual machines or VMs rely on a hypervisor. Examples include VMware VirtualBox or Hyper-V to emulate an entire set of a physical hardware for each instance. So when you spin up a VM, it boots a full guest operating system, whether it's Windows, Linux, or whatever, which in turn initializes its own kernel, drivers, and system services. This approach provides a strong isolation, yes, but it comes at the cost of significant resource overhead. Because if you think about it, each VM consumes dedicated CPU cycles, RAM for the guest OS, and disk storage for its virtual disk image. As a result, starting or stopping VMs can take tens of seconds or even minutes, and running large numbers of VMs on a single host often leads to wasted capacity and slower overall performance. By contrast, containers, they share the host's operating system, kernel, and rely on two key Linux features. First, there's namespaces for isolating network process trees and file systems, and then there is control groups for limiting and accounting resource usage. These are used to keep applications separated. So rather than booting a full OS, a container packages just your application code, its libraries, and its runtime dependencies. The slimmed down approach means containers require far less memory and storage and can start in a fraction of a second. When you need to deploy dozens or even hundreds of microservices, containers' rapid startup times and low overhead let you scale horizontally with minimal resource waste, making them the clear choice for modern cloud-native architectures. What you need to retain from all of this is summarized in this table. So virtual machines having a full OS per VM have a higher startup time and more resource overhead than containers that share the host OS kernel. Why do tech giants like Google, Amazon, Netflix use containers at scale? It's precisely for the benefits you see now. Portability, it accelerates development cycles by removing configuration drift. Isolation, it simplifies debugging and enhances security by restricting each container's access. And the sheer efficiency means you can achieve high density, getting more work done with fewer servers. For startups and enterprises alike, this translates to faster innovation and lower infrastructure spend. Onto Docker now. Docker it's an open source platform for building, deploying, and managing containerized applications. Before Docker, different dependencies often caused inconsistent results, as you can see in the example here. Docker solves this by packaging code and dependencies together, ensuring consistency across environments. Thus, developers they focus on coding without worrying about the environment, while ops teams handle deployment without worrying about the application code. Let's start with the concepts you need to know to work with Docker. A Docker file is a script with instructions to build a Docker image containing all that the environment needs to run the app. Let's have a look at the Docker file we will use in our application later on. Here the assumption is that we have a Flask Python app, app.py, which we want to be able to run anywhere. So we created this Docker file to construct an image for the app and its dependencies. First, in the first step, we take a base image, which in our case is a Python image. We set app as the working directory in the container and use requirements.txt to install our dependencies via pip. We then copy the rest of the application code into the container. Finally, we're documenting port 5000, the port where the app will be running, and then finally we are running the app. A nice feature is that if you had to change the Docker file and rebuild the image, Docker only rebuilds those layers that have changed since the last build. This is highly efficient as it avoids the need to recreate the entire image from scratch every time. Now, how do we go from that Docker file to a Docker image? We simply use the docker build command. Docker will build a layer for each separate instruction, and all these layers together will form the image. The image is a read-only template at this point. Now that we have our image, we can use it to run containers. This is done through the docker run command. So a container is simply a running instance of a given image. It's a lightweight and isolated environment. All such running instances of the same image are consistent and they all contain all that they need to run smoothly. No more but it works on my machine problems. Now what if I want to store this image somewhere? I built it locally and we all know how risky it is to settle here. What if I want to share it with others? For that, we use Docker registries. A registry is a server-side application to which you can push images and from which you can pull images to use. Think of a registry like a library, and each image is a book in that library. Just as libraries have systems to manage the storage, cataloging, and retrieval of books, a Docker registry handles the images, and when developers need to push new images or pull existing ones for deployment or development, they interact with this registry. Docker provides a public registry called Docker Hub, which hosts a vast array of images for public use. This includes official images for operating systems, databases, and programming languages, among many others. This registry, the Docker Hub, is where we put the base Python image we used in our Docker file on step 1 from. However, companies often require a private place to store images, and these images might contain proprietary software and configurations. For this purpose, Docker, as well as other like third-party vendors if you want, offer private registry solutions that can be hosted on premises or in the cloud. Now let's see what actually happens architecturally. The CLI communicates with the daemon over RESTful API. When you run, for example, Docker run, the daemon checks local images or pulls from a registry. It then instantiates a container. Docker Compose and Docker Swarm extend Docker's capabilities. Compose orchestrates multiple containers on a single host, while Swarm clusters hosts into a single virtual Docker host. In enterprise settings, many teams also evaluate Kubernetes, but Docker Swarm remains an excellent starting point. Let's go over the terminology we used here. Docker daemon, it runs in the background on the host machine and listens for API requests and manages images and containers and networks as well as volumes. The CLI, it's a UI to interact with the daemon via commands. Images, as we previously mentioned, are read-only templates to create containers, and they're stored in layers. The registry stores images, allowing image sharing and distribution. And containers are runtime instances of images. They're mutable, isolated environments. Docker Compose is a tool for defining and running multiple containers applications, while Docker Swarm is a built-in native clustering for scheduling containers across multiple nodes. These commands form your daily Docker toolkit. Pull fetches images, run instantiates them, ps lets you inspect all that's running, and cleanup commands like stop, rmi, they keep your environment tidy. Remember that removing containers or images that are still in use will fail, so you may need to stop containers before removing them. Finally, let's get our hands dirty with Docker on the free platform Docker Playground, where we will deploy a basic Flask Python app. In the next slide, here you can see exactly the content of the files we will need to, and which we will use to deploy our app. So navigate to this website, labs.play-with-docker.com, and click on Start. This will open a session just for you to play around with Docker. First, click on Add a new instance. You now have your first node, Node 1. It's a virtual machine. You can check its OS by looking up cat etc os release. We're currently in the root directory. We're gonna create our own directory to put our app in. Then you're gonna create the Docker file app.py and requirements.txt inside of this directory. You can copy-paste the content from the presentation. Let's go through our app.py. First, it's gonna import the Flask class, then it's gonna create an application instance. The decorator is gonna bind the function below to the root URL, and this function executes on each GET request to this path, returning our message. And finally, app.run will launch the built-in development server, listening on all network interfaces so Docker can route traffic into the container. Let's go over our Docker file one more time. It's gonna use a slim Python 3.11 base image to keep the image lightweight. We're gonna set app as a working directory inside the container. Then it's gonna copy requirements.txt and install dependencies with pip. It's gonna then copy the rest of the application code into the container and document port 5000, which the Flask app listens on. And finally, it's gonna specify that the container should run python app.py by default. When we execute our docker build command to build an image from this Docker file, for each of these steps, there's gonna be a new layer. So let's launch our docker build command. We're gonna type docker build -t so we can give it a name and optionally a tag. We're not gonna give it a tag in our case now. We're gonna give it one later on. And I'm just gonna name it Flask demo. Then we're gonna put a dot indicating that our Docker file is in the directory we are currently in. And our image is now built. To double check, we're gonna execute docker image ls, which lists all our images. And this is it, our Flask demo image. Now let's run a container using this image. We're gonna type docker run forward ports 5000 to 5000 inside the container, which is where our Flask app will be running. And its name is Flask demo. Our Flask app is now running. How can you open it and actually see what it renders? You click here on open port and it's already suggesting port 5000.
2 hours later.
And after a while you will get hello from Docker. Now press on Ctrl C to stop the running container. To make sure our container has successfully stopped and there are no running containers, we execute docker ps. So no containers are currently running. If you execute docker psa, it will show us that our previous container, the Flask demo app, was created 4 minutes ago and it exited just a few seconds ago. Now yes, we have this image locally. We want to push it to Docker Hub, to our own registry. How do we do that? First, I need you to navigate to hub.docker.com and create your own account if you haven't already, and sign into it. And retain your username. Then go back to your node and execute docker login to log into your own account. You're gonna navigate into this URL and use the one-time device confirmation code you provided. When you get login succeeded, you can proceed. Now we're gonna tag our existing image, so Docker Hub recognizes it. You're gonna execute docker tag the name of your current image, which in our case is Flask demo, your Docker Hub username, which for me is Joel Humsi, / Flask demo, and we're gonna add a tag which is gonna be latest. Now that our image is well tagged, we can push it to Docker Hub. This is done through the command docker push. followed by your images tag. Now that our image is well pushed, we can check it here in Docker Hub. When I refresh, here it is, Flask demo. It was pushed less than a minute ago. So now anyone is able to pull this image from my repository and then run a container with it. So let's recap on today's Docker session. What are the key takeaways? We learned that an image is a blueprint for containers. Containers are lightweight and scalable, and they package apps and dependencies consistently. Docker ensures consistent and portable environments. It simplifies building, sharing, and running containers. Its architecture includes key components such as the Docker client, Docker daemon, and Docker registry. Docker Swarm enables clustering and scaling across nodes. And don't forget that the Docker file is simply a script to build an image which you can then use to start up containers. Thank you so much for attending this session. I hope it was fruitful.